Hello students, before we jump into the idea of the electromagnetic induction, we need to develop certain ideas and work on some definitions, out of which first we have to deal with the concept of the magnetic flux. This idea of the magnetic flux is same as you have learned in the case of electric flux. The only difference is that you will use magnetic field here in place of electric field, right? Now, I hope you also remember the concept of vector area. Now, what is that vector area? So, basically, when you associate any directional element with a scalar quantity, so that becomes a vector. See, here, if I have this plane, and suppose this plane has an area A, right? So you will write the area in meter squares. But if I associate a unit vector, and that unit vector is perpendicular to the plane of this area, means this unit vector is perpendicular to this area, so I can define this area as area vector, and I can represent it as A equals A n cap. Now this has become an area vector, right? Now coming back to the concept, just like the idea of the electric flux, we are defining the magnetic flux as the number of field lines. Which field lines? Magnetic field lines that are passing through a given area in the direction perpendicular to the area. Now see, this is a plane having area A, and suppose it is placed inside some uniform magnetic field. So I am drawing field lines corresponding to this magnetic field, right? Now, suppose this magnetic field is making certain angle, say angle theta, with this unit normal, right? Now, the component of this magnetic field in the direction of the unit normal, what that would be? So that would be B cos theta. So that component is basically the perpendicular component. Similarly, we have the horizontal component, that is B parallel, so that is B sine theta. But we are interested only in the magnetic field that is perpendicular to the area. So considering this idea, just like we have described the idea of the electric flux, now if I want to calculate the magnetic flux through a small elemental portion, let this is the small and elementary portion, let the area of this elementary portion is dA, and this normal is same corresponding to this area also. So the small amount of electric flux, that is represented by d phi b, b means magnetic field, so the small amount of magnetic flux that is passing through this area is given by the product of the component of the magnetic field that is along the normal, that is B cos theta, or you can say that is a perpendicular component, times the area you are considering. So this product of the perpendicular component of the magnetic field and dA, both are describing the product, their product is describing what? The magnetic flux, right? And if you want to calculate the magnetic flux corresponding to the whole area, so what you will do? You will integrate it. Clear? So if I want to write the complete flux, so I will write the complete flux corresponding to the whole area. So I can write it like that: B cos theta dA, or you can write it as B perpendicular component dA, and also you can write it as B dot dA. Now what is that dA? dA is this. I am writing this corresponding to the vector area. So this is the definition of what? Magnetic flux. So from here we know that the unit for the magnetic field is Tesla, right? And for the area, the unit is meter square. Clear? So if we have a magnetic field of 1 Tesla that is crossing an area of 1 meter square, we call this as 1 Weber. So what is the unit of magnetic flux? That is 1 Weber. So we represent it by WB, that is 1 Tesla per meter square, right? Also, we can write 1 Tesla as 1 Newton meter per ampere, and here we have the meter square. So finally, what we will get? 1 Newton per ampere meter. So that is also the unit of magnetic flux. Also, in electric flux, what we have learned that flux can be positive or negative. So just to brush up that idea, so I am again writing it in a general form. See, this is a general surface. That surface is enclosing some volume. Suppose this surface enclosing certain volume is placed in some magnetic field. So this is any generalized magnetic field, right? Now, what I'm interested in calculating the flux that is associated with this surface. For that, what I will do, I will consider elementary areas such that this elementary area has area ds, this elementary area has ds. Also, you have to remember that whenever you take the normal corresponding to a surface or an area, that you have to always draw away, that you have to always draw away from the surface. You will never draw it inward. You will always draw it in the outward direction, right? Now you also know that when you consider the magnetic field corresponding to magnetic field line, that magnetic field is always tangent to the magnetic field line at that point. So the magnetic field will be in this direction. Now here, if you look here, so here the angle between this normal and the magnetic field, this angle is acute angle, means less than 90 degree. And here, if you see, that angle is obtuse angle, that is greater than 90 degree. So let me write, this angle is greater than 90 degree. And this angle theta is less than 90 degree. Okay. Now the flux corresponding to this section. So I will write the small amount of flux that is equal to B into what? ds cos of theta. Similarly for here, if I write d phi, the small amount of flux that we can associate with this area is B ds cos theta. Now as theta is less than 90 degree here, so this value of cos theta is greater than 0, means positive. So you will say that the flux is positive. But here, as the theta is greater than 90 degree, so cos theta greater than 90 degree, so the flux will be negative. This means if the field lines are entering a surface, if the field lines are entering a surface, the associated flux is negative. Similarly, if field lines are leaving a surface, then flux is positive. Clear? So you have to understand these two basic ideas also. Now, in order to understand it in a much clearer way, so let's solve a problem. Now, this is a problem corresponding to the concept of magnetic flux. We are given here with the magnetic field that is acting along the x-axis, means this is I cap. What you have to do, you have to calculate the flux of this field through a square of side 10 centimeter whose plane is parallel to YZ plane, right? So let's draw this. This is x-axis, this is y-axis, this is z-axis, right? So it is given that magnetic field is along x-axis. So magnetic field will be in this direction. So this is the magnetic field, 3 into 10 to the power 3 I cap Tesla. Now we have a plane that is parallel to YZ plane. So this is the plane and this is a square plane. Each side is of 0.1 meter. So what you have to do, you have to calculate the flux through this plane. Now, first you will calculate or find the area vector. And area vector, the normal is always outwards. So area vector will be what? The magnitude of the area and the corresponding directional element. Now, it is clear from here that the directional element will be along x-axis. So we will put a cap. So area is how much? 0.1 squared, because it is the area of the square I cap. So that is 10 raised to power minus 2 I cap. So if I want to calculate the flux will be B dot A, the total flux through that loop. So that is the dot product of magnetic field and the associated area vector. So if I substitute the values, 10 raised to power 3 times 10 raised to power minus 2 I dot I. So what is I dot I? So that is equal to 1. So finally we will get 30 Weber. So that is the flux that is associated with this surface, right? Now in the B part, what he is asking, what is the flux through the same square if the normal to the plane makes an angle 60 degree with the x-axis? Now see, what does this mean? Suppose you have tilted this area such that the normal to it is now making an angle of 60 degree with the x-axis. So this is x-axis, right? Now in order to calculate the flux, we know that we have to find the product of the perpendicular component of the magnetic field corresponding to the area times area. So what is the perpendicular component? That is B cos theta times A. So what is B? B is given, magnitude of B is what? 3 into 10 raised to power 3 cos of theta. So theta is basically the angle between the normal and the x-axis. So it is given 60 degree here. And area, we know that is 10 raised to power minus 2. Now cos theta is 1 by 2. So finally we will get 15 Weber. So that is the clear. Now from here, in the subsequent situation, you will also come across two special cases. Suppose this is the uniform magnetic field given to you, that is represented by equally spaced lines. Suppose I have a loop having area A and that is placed in the plane of the magnetic field, means the magnetic field lines are passing like that. So corresponding to that area, the normal is in this direction. So there is no component of magnetic field that we can associate in the direction of n cap. So in such a case, the flux would be B A cos of 90 degree, because the angle between the normal and the magnetic field is 90 degree. So we will say that flux will be 0 in such a situation. Now suppose if I rotate that area, then magnetic field lines will completely pass through, and the normal to this magnetic field, normal to this loop is along the magnetic field. In such a situation, the theta is 0 degree and flux would be BA cos 0 degree. So flux will be equal to B times A, and flux will be maximum in this situation, right? So I hope you have got the idea of what is magnetic flux. So magnetic flux is basically the product of the perpendicular component of the magnetic field that is passing through a given area, or you can say the total number of field lines that are passing through a given area in the direction perpendicular to the area. So we are only interested in that magnetic field that is perpendicular to a given area. So in this way, we have coined a term magnetic flux. Now that concept of magnetic flux will help us to understand the ideas of electromagnetic induction.